Okay, okay. I just muted myself. Okay. So Honglu, can you do the recording and let's start?
I have started recording.
Yeah, that's great. Okay. So let's begin. Okay.
Good evening, everyone. The paper I present today named as FedAT. The AT means asynchronous tiers. It is used in this paper to solve the stragglers problems. And this paper comes from the group from GMU, and the author Zheng Chai has also proposed another paper named TIFL. It's also use tiers to solve the stragglers. And the paper is published in Supercomputing 21. In traditional synchronous federated learning, in each communication round, the server will randomly select a subset of local inputs to perform the local training. But the synchronous federated learning, such as the Fed average, cannot perform well on heterogeneous federated learning environment. And also, when there are some stragglers, for example, some slower clients in the system, the synchronous federated learning cannot perform well. So based on the synchronous federated learning, some researchers has proposed the asynchronous federated learning. Different from synchronous federated learning, in asynchronous federated learning, whenever a client finishes its training, it can update the local model to the server. So there is no communication round in the asynchronous federated learning, and it can solve the straggler problems. And the asynchronous federated learning has also some disadvantages. For example, in the FedAsync proposed in this paper, the server needs to communicate with all of the local devices at each at each round, and here comes the communication bottleneck. Because all of the local devices need to communication with the server whenever they finish their training. So the communication cost may be very high. And also the global model may bias to some devices which communicate with the server more frequently. So to solve these two problems, this paper proposed the FedAT. And the FedAT can be seen as the combination of the synchronous and the asynchronous federated learning. And it uses a tiering method. And the FedAT aims to solve both of the stragglers and also the communication bottleneck. It can reduce the communication cost. And here is the figure of the FedAT. We can start from the clients. First, we do some profiling to divide these clients into some tiers according to their training latency. The training latency can be seen as the sum of the communication time and also the computation time. And you can see in this figure, there are M tiers, and the tier 1 is the fastest tier, and the tier M is the slowest tier. And after that, all of the tier can do the local training. The server can select some clients of the server can select some clients in a tier, and the tier can do the selected clients can do the local training, and then they can do the comparison. They can compress their local models and upload all of the local models to the server. You can see when the time T1, the tier the tier 1 finish its local training, and all the local models are comprised and then uploaded to the server. And then the server do the decompression, and the server can use the local models from the clients in tier 1 to generate local updates of the tier 1. You can see the red one, the W tier 1 T1. And then the server can use all of the W T1 to generate a global model. And in the time T2, the second tier can upload their local models to the server, and the server do another global aggregation. And then the server can send the global model back to the ready tier. And in this figure, the ready tier is the tier 1. So the tier 1 can do another round of training. And to start the training, the first step is the profiling. And this paper...
Could you go to the previous page? So across tier, will the server do anything across tiers?
You mean the aggregation rules?
Yes.
Yeah, they propose a new aggregation rule that the more frequent tiers has a lower weight when
for the overall aggregation, right?
Yeah, to reduce the bias to some.
I guess so. No, okay. Okay, thank you.
Yeah, Honglu, take a deep breath. Okay, don't be too nervous. I can still feel, like you cannot like catch your breath. Okay. Calm down, okay, calm down, and slow down. Try to speak slowly, and don't be nervous. Okay. Okay.
And the first step is the profiling. And the profiling step in this paper is the same way as the profiling step in TNFL. They also propose two kinds of profiling methods. The first one is the offline profiling. In offline profiling, the server can decide some times, for example, the time T1 to time Tn. And in time within the time T1, the clients which can send back the local models successfully to the server can be divided into the tier 1, and then we can divide the clients into n tiers. And for the online profiling, the server can send some tasks to all the devices and to compute the communication time and also the computation time. But in this paper, the authors only consider the offline profiling, because this paper assumes that once a client belongs to some tier, it will not belong to any other tiers. It will not change into any other tiers. And for the local training, because of the non-ID data in real world, the frequent local update may cause the local model to diverge. So due to the varying updating frequency of the different tiers and also the data heterogeneity. So to reduce the divergence of the local updates, the authors proposed some constraints. You can see in the first equation, the FK WK is the loss function of the Fed average. And here the authors propose a constraint lambda to guarantee that the local model will not diverge diverge very much from the global model. And based on the advanced local objective function, we can generate an objective function for a tier. In the second equation, the nk means the data examples belongs to the client k, and the st means the selected clients in the same tier, and also the nc means all of the data examples of the selected clients. And just as the Dr. Pan said, to solve the cross-tier weighted aggregation, we need to guarantee that the global model will not bias to some more frequent clients. So we need to assign some higher weights to the slower tiers. So the authors proposed a cross-tier weighted aggregation. You can see the objective function of the whole training. The T tier 1 and the T tier 1 means the communication times, the times the tier 1 communication with the server. So for the tier 1, it's the fastest tier, so the T tier 1 will be much higher than the T tier M. And in the objective function, you can see if we choose for the tier 1, it has a much lower weight compared with the tier M. So this objective function can guarantee that the global model will not bias to the tier 1. Okay, any questions till now? Okay. So
Honglu, I'm sorry. So where is the weight you're talking about? Is a relative weight? Okay, the weight determined by the time, by the frequency, right?
Yeah, the T means the communication times.
Okay. So the big T is the overall time, right? Okay.
Yeah.
Okay.
So if the tier has a higher frequency, it will has a lower weight.
Okay, thanks.
And here's the whole algorithm. And you can see the advanced objective function is used in the algorithm. And the function weighted average is the proposed cross-tier aggregation rule. And to solve another problem to reduce the communication cost, first, the authors claim that due to the divergence of the non-ID data, some model comparison method, for example, the quantization, may lead to some huge errors because the local models from different clients can be very different. So the author used a kind of data comparison method in this paper. They used the encoded polyline algorithm. And the encoded polyline algorithm is a loss compression algorithm. And it is used in the Google Map plat. And it can convert a series numbers to the single string. And here is the definition of the steps of the encoding polygon algorithm. In this algorithm, to conserve space, so the points only include the offset from the previous point. So it can save some storage space. For example, in these steps, we can convert the weight parameter into some decimal values and then convert the decimal values to a string according to the ask encoding method. And here's an example. There are 3 points. You can see in the change in the 5th column, the change in latitude, it only considers the offset from the first point. And we can change all of the 3 points into a string. And in this, if FedAT, the authors used this encoded polygon algorithm. So the comparison process can be divided into some steps. First, the FedAT can flatten the width of each layer to get a list of decimal values. Because the FedAT is implemented based on the TensorFlow, so you can use some flatten functions. And then we can use the polygon encoding to convert every decimal value into a compressed string and do the upload or download transformation. And then in the server, it can do the compression and then reshape the decimal values back to the weight. And the next part is the experimental part. The authors use 5 kind of data sets in their experiments, including some data sets from the framework Leaf. For example, the feminist. And for different data set, they use different kind of machine learning models. But all of the models is not complex. It's just simple CNN or RSTM. And the authors compared the FedAT with 5 federated learning methods. The second method, the TNFL, is also proposed by the authors. It means we can divide all of the clients into some tiers, and in each communication round, we can select the clients from the same tier test to reduce the straggler problems. And in FedProx, the local clients can train local model. The server can decide the local epochs based on their computation capability. And in Fed asynchronous, it means all of the clients will take part in the global training. And then whenever they finish their local training, they can send their local model back to the server. And just as I said before, the FedAT is implemented based on the TensorFlow. And the authors divide all of the clients into 5 tiers with delays of 0 seconds, 0 to 5, 6 to 10, and 20 to 30. And the authors also randomly select 10 unstable clients from 100 clients, which could drop out and will never come back again. Here is the total prediction performance. The 2, 4, 6, 8 means the number of the classes for the non-IID distribution. And we can see the FedAT has a better performance on both non-IID distribution and the IID distribution. And this one evaluates the training time of these file methods. And we can see the FedAT has a when they achieve the same accuracy, the FedAT spends less time. And this one evaluates the non-ID level, just the number of the class of each data set. And they also evaluate the communication cost. The table is the data uploaded. The data need to upload it to the server when we get some accuracy. For example, in the first column, it means when the accuracy is 0.5, the FedAT needs to upload this data to the server, so it can reduce the communication cost. And you can also see from the figure that when the test accuracy is the same, the FedAT will upload the least data. They also evaluate the trade-off between the accuracy and the communication cost. Here, the precision 3 means in the encoding polyline algorithm, there are 3 decimal places. So there will be some loss for the loss of the information sent to the server. So when the precision is 3, you can see the performance is quite worse.
So for this, did they compare, say, if they're using the coding scheme, compare with quantization with the error control? You know, literature has a lot of paper talk about, we can do the quantization with the error control. I think most of them performance pretty good. So did they do any kind of comparison? Yeah.
They don't do the comparison. They just claim that this has a better performance on non-ID data.
Ray, are you there? I think you have read more quantization paper than me, right? So you have any comments on this?
I have a question. For each of the line, the precision 3 and 4, they are all the same for all the tiers. They choose the same quantization level.
No, the precision does not mean the quantization level. They use the coding scheme to do the compression.
Yeah. The strategy is all the same for all the users. I mean.
Yeah, it's the same for all of the users.
Okay. I mean, the compression they use is pretty new to me. I'm not familiar with that algorithm.
Yeah, it's kind of data compression, and I think.
Well, what is the benefit of using this type of compression?
They claim that if we use the model compression methods, because of the heterogeneity of the local data, the local models will be very different. So they claim that
But here they're not doing the weight quantization; they're doing the gradient quantization, right? For the gradient quantization, we have similar quantization peer scheme. I somehow know the coding things they're using, because we used to work on the location privacy stuff, but we use a different approach to compress or to change the longitude and the altitude into one number, right? So we use hash function stuff, but whatever scheme you use, you have a certain kind of loss, right? Just like in this one. So I think Ray's question somehow makes sense. I mean, you use this one, you have a certain kind of loss. You use the gradient quantization, you also have loss. If you don't do the comparison, how can you justify, the coding scheme they're using there will be better than the quantization, the widely used quantization scheme? That's the question.
As far as I know, if we're doing the quantization, for example, we're using the model compression, then like model pruning or model like the weight quantization, usually it will involve the training, right? We do the model pruning or do the quantization during the training. Then because the non-ID data distribution on different clients, then the pruning or the quantization may applied to different parameters. Then after we aggregate different local models together, we do the average. Then sometimes, I mean, for the same position, position in the model weight, some of the the parameter will be quantized, or some of the weight will be pruned. That's why Honglu mentioned if we do like a model pruning, it might be.
Yeah, Dr. Wang, I agree with you. That's weight quantization, right?
Right.
I'm trying to get, so where they apply this coding theory, they apply that on the training data, or they apply this coding theory for the, say, the gradient updates, transformation.
I think it's the gradient, the gradient data doing the transmission.
Yeah, if it's a gradient transformation, similar compared to the weight quantization, we also have gradient quantization, right?
Right.
To compress the gradient data.
Right.
That's exactly similar to this one, right? We process the data only. We don't touch the model, right? So yeah, that's my question. I mean, you use this one to compress the data for better transformation. Gradient quantization also follows the similar idea. You compress the data. You quantize the data. Anyways, in general, it's compression. You compress the data and transmit. So we need to say the difference there. Whatever we have loss, right? For this one, we have loss. It depends on the procedure you choose. For gradient quantization, the same. Depends on which kind of weight, I mean, bit of quantization you choose, you have loss too. So
I think this is the main drawback. One of the main drawback of the paper, because the paper doesn't clarify the motivation of why we should use the polyline algorithm rather than other, compression algorithms.
Exactly. For example, the top K also can be used, right? So there's a lot of compression techniques there. You need to justify, right?
Yeah, because the compression algorithms are like have been studied for decades. A lot of different algorithms for compression and different trade-off, right? So I really don't know why this paper choose this algorithm, and it doesn't give a very, doesn't give like a clarification at all. It only claimed, okay, we are better than those model compression because we don't need to, we won't like mess up with the aggregation because we apply to all the model, all the numbers, all the parameters. And I think later Honglu will also introduce another drawback. This paper is interesting, but it played a lot of like tricks in. So.
But yeah, the layer-wise, the aggregation, that one is simple, but it's very interesting, like you said. So I like the idea.
You mean the tier, right? The tier-wise.
The tier one, yes, the tier one.
Yeah, but the tier-wise, the idea has already been proposed by the previous paper, the TIFF, right?
Okay, I don't know that. Oh yeah, the contribution.
It's probably because the paper published, in supercomputing. This conference is more like focused on high performance computing instead of like distributed machine learning.
I know. I see. Yeah. Okay. Okay. Yeah. I just have doubts about this one. Yeah.
Right, right. Yeah, same here. Yeah.
Move on, please, Honglu.
Okay. The next experiment is the evaluation of the weighted aggregation rules. And the authors compares the weighted aggregation with the uniform aggregation. In the uniform aggregation, it means different tiers has the same weight, and so the global model will bias to the more frequent tiers. And you can see the weighted aggregation rule has a better performance. And the authors also do the large-scale training based on the dataset MINIST and also the dataset Reddit. And they do the training. I think the large-scale training include 500 clients, and they do the training based on the AWS virtual machines. And the authors also evaluate.
Here, could you go to previous page? I have a non-related question. Have you used the AWS EC2 virtual machines before? Have you guys used that before? No?
I haven't used it before.
Yeah, just try to figure out how do they evaluate the communication things.
You mean the communication between the EC2 machine?
Yeah, say, I know probably it's better than simulation, right? But still, it look like internet connected. It's still.
So it depends on what kind of scenario. If you wanted to use the AWS EC2 to simulate or to approximate the internet for federated learning, it might not be practical, because if you have machine in the same, like we say, like a VPS or the same data center, they are using the internal data center network. It's very stable. The bandwidth is also really very high.
Yeah, that's exactly the question. So, okay.
If you're using like a virtual machine, or like a instance in two different regions or two different data centers, then it could be public internet. I did some test before. They do have fluctuation, and there are some patterns, but for this traffic between two different data centers over the internet, we need to pay. Okay, for example, like 10 gigabytes, you need to pay some money for this traffic.
So what's the one advantage of this EC2 virtual machines? They have unlimited computing resources. That's the
right.
same.
So you mean? I don't recommend people to run the federated learning experiments using EC2 unless you want to have a really high or very large scale, right? For example, they have like a 100 machine. We can build a 100 machine by ourselves, right?
Okay. Yeah, because we are working more on the wireless part of this machine learning, right? So, like you mentioned, we try to measure the delay or energy. So yeah, that's the reason why I believe this EC2 is more like a huge simulation.
Right.
Things for
so
me.
Instead of like using EC2, I think you can buy some like a 1 or 2 server and run the wireless simulation there. I think that'll be the same, right?
Yeah, we do have that, but
right, yeah.
We cannot run large scale. We have some reviewers comments say it's a small scale, is a 5 device only. why you guys don't do like large scale evaluation?
Yeah, if you want to have like a large scale, then either go to AWS or you go to like some high performance computing cluster. I think every university has some HPC cluster, right?
True, but that one we cannot do the wireless measurement, right? So we can only do the internet.
but using EC2, you cannot do the wireless environment either.
That's true. That's true. Yeah.
Right.
Yeah. But you compare that to some theoretical analysis and you draw a figure or curve. So what EC2 offer you more? EC2 offer you more, or is it basically the same thing? Same.
What do you mean by more? More like,
I don't know, if you do some theoretical analysis, say I draw a curve with the increase of computing resources, it's going to look like this.
well, what kind of like a theoretical analysis?
Yeah, I'm trying to figure out what I'm trying to say here. Oh yeah, probably if you want to know the testing accuracy stuff, yeah, we have to use that, right? Okay, okay. Thank you.
Okay.
And I believe the authors in this paper also used the simulation, because they mentioned that you can see the first one, they just decide the delays from decide the delays for random select some times per second.
That's true.
Okay. The next experiment is the number of selected of clients, because
Honglu, have you mentioned that they are using the CPU instance instead of GPU instance?
Yeah, all of the experiments are based on the CPU environment.
Yeah.
And I believe that using CPU can takes more time on the training. So it seems the FedAT has a better performance than the other methods.
So they don't use GPU, instead they use like a CPU machine. Then the local training time can be longer, and eventually the performance compared to other solutions could be better because they're using CPU.
Yeah.
I think this is a trick, right? This is a trick that played here.
But another thing is, this paper is like more communication efficient learning paper, right? They divide the things into tiers, try to
right.
It is a straggler. So did they mention? Oh, they mentioned the time, communication time. Okay.
But when they show the performance, they show like a end-to-end training latency. The training latency will include the training time and also the communication time and also the compression time. But the paper doesn't break down all the latency. They put all these kind of like different latency of different stages together and say that they are the best.
Yeah. Also, again, I have the concern. I mentioned that so many times. If the computing time delay and the communication delay, they're the same level. I think if you run big models, CFR10 is okay. If you run big models, it should be more than 10 seconds.
Right.
Something, right? So in that case, I think your computing would be dominant factor instead of communication.
Right. And another concern is if we have very complicated model like ResNet, then I mean the compression algorithm will spend a lot of time to compress the model. Then I don't think, I mean, there could be like a trade-off, right? The compression time and the communication time. Then if the model is large enough, I think the increase of the compression time will be like far beyond the decrease of the communication time, probably.
Yeah, I get your point here, yeah. But it really depends on which kind of compression algorithm you're using.
Right.
Also data set, like you mentioned.
And the precision level, right? How much loss we can allow here.
Also transmission speed and gradient size and computing. Anyway, if the computing time, compression time, communication time, they're comparable, we can talk about the trade-off here. But if one of them are dominant, we got to deal with the dominant ones. The other two is meaningless.
Right. Yeah, exactly.
Yeah, that's the reason why we question why so many papers talk about communication efficiency if computing is the dominant factor. In particular, they use the CPU here.
Right, right.
Okay.
And the last experiment is the distribution of clients numbers in different tiers. Here, they use 4 distributions, and for the uniform, all of the tiers has the same number of clients. And for the slow tier, you can see for the slow distribution, you can see there are 200 clients in the tier 5. So there will be more slower clients. And for the fast distribution, there will be more faster clients. There will be more clients in the faster tiers. So because of the faster tiers has a lower weight when do the aggregation. So the fast distribution has a worse performance compared with others. Yeah, and this paper, I think one of the problem is that the authors didn't consider the clients with some varying communication capabilities. For example, I think some clients can change from the tier 1 to tier 3 because of the change of their communication environment. And the authors just assume that all of the tiers will be in the same, all of the clients will be in the same tiers during the training. So I think that's one of the disadvantages of this paper. Yeah, that's all. Any questions?
So I want to add up a little bit to respond to the question made by Dr. Pan. When we talk about the level of the communication time and the computation time, which one is like a dominate? If we can perform some federated learning with real forms, right, like Android forms, we probably can have a better understanding of this problem.
I mean, that's true, but it's also, even you play with TX2, because my student have played that for a while, we can still find the cases, most of the time, computing time is dominant. Even we have relatively very high transmission rate like Wi-Fi 5, we can go for like 50 Mbps. Computing is dominant, right? Computing consume more time. I think my student Huayan and Ray, they have done a lot of experiments.
But what about like what is the level compare? So for example, the computation time will be like 1 minute or 10 minutes, and the communication time will be like around 1 second.
It depends on the model and data set. Sometimes you can find a comparable case. Sometimes you cannot find a comparable case.
Okay.
But say if you under the assumption the transmission rate is really slow, like we use 4J, or like in the paper we assume 4 Mbps to 8 Mbps. Yeah, we can find some comparable case.
Okay.
But if you consider the transmission speed is high, like in the future, the 5G or Wi-Fi 5, Wi-Fi 6, most of the time computing delay dominant. Even you use TX2. If you move that to smartphone, computing consume more time. That's based on our experiments, right? So that's the reason why I don't know. Also, it really depends on your gradient. Some of the models, say like VGG, they have a large gradient. Some of the model, they have a small gradient. So that also affects, which one will play most important roles in the time consumption too. Yeah.
Okay.
So that's the reason why we question when we always talk about communication efficiency things. I don't know. Probably they can consider a very huge model from the server. If it's a server, very huge model, they talk about internet connection. I'm not sure if still that's the case, because the internet connection is still be fast, right? So yeah, your gradient size increase exponentially probably, but I'm not sure if still communication is the bottleneck or computing is a bottleneck. It's hard to say.
Okay, I see.
Yeah.
Yeah. Okay.
At least for wireless, it depends on the situations, right? Yeah. We submitted a paper to Mobisys this year. Unfortunately, it got rejected, but you know, still we articulate this kind of issue. Yeah.